So welcome to lecture 19 of MCS 320. So this is a pre-recording scheduled for Friday, 8 July. So this is already our lecture 19. So the previous two lectures were occupied by the first midterm exam. So in this lecture we start a new chapter and in essence also a new part of the course. So we will look into the definition of mathematical functions, and we will recall the concept of symbolic evaluation. So we have actually already treated expressions as functions, and functions in symbolic computation are actually nearly as indistinguishable from expressions. That's the main point of the first part of the slide presentation. In the second part, I will address some special functions. So when we think of functions, we might think of continuous ones, but there are many functions which are discontinuous, and we can model them with step functions. Okay, so functions are expressions in symbolic computation. So in particular, when we are using SageMath, where expressions are defined like in an object-oriented fashion, using the Python language, then they are callable objects. That means that we can evaluate them. So just to make clear that when we speak of evaluation, we can indeed evaluate numerically, replacing all input parameters by numbers, and then we also get a number on the return. So that's what one may think naturally about evaluation. But in symbolic computing, we can do much more. We can substitute the names of the input parameters by symbols. And then the result is again another expression or another symbol if it simplifies. So that kind of explains why functions and expressions are extremely similar. So if we take an expression and we substitute symbols in there, then that expression can be very easily turned into a function. And the symbolic evaluation of a function, if you have given a function, then if you evaluate into symbols, you get an expression back. Okay, I titled the name of the chapter Calculus because this is where one encounters mathematical functions very naturally. And as programmers, we are defining functions, but mathematical functions or functions that we consider in symbolic computation, they have special functional attributes. So we can compute derivatives. So the derivative is the instantaneous rate of change. So here I wrote the limit definition. The opposite operator of the derivative is the antiderivative, also known as the integral. So then when we apply the integrand, we actually don't get the original function back, but because the derivative of a constant is 0, then one gets it up to a constant. So the antiderivative is very useful when one computes areas. So there's also a very natural geometric interpretation of this, and this integral symbol here can be seen also as a limit, as a stretched sum symbol. So the difference between the Python functions that we will see in the second part when I get to SageMath, and the Python functions on one hand and the functions in symbolic computation on the other hand are precisely these two methods, the uh, derivative method or the diff operation, and then the integral operation or the antiderivative, um, as we have defined here on this slide. So that's an important distinction to keep in mind. Okay, so then step functions are this continuous function. So here is one prototype. So that's the unit step function. It takes only two values, so you could also consider it as a switch. It's either off, 0 for all negative values, or 1 for all positive values. So you see the plot. Perhaps I should have used a little bit thicker lines. But what I did not define is what happens at the origin. So one can leave it undefined, or one can even say that the function value can be any value between 0 and 1. So you can either flip it to 0 or 1 if you have to pick a value. I will try to indicate that we can see the unit step function as the limit of a continuous function. A continuous function that passes to 1/2. So if one wants to define what one calls the Heaviside function, then as the limit of that continuous function, a natural definition is then to work with 1/2. Okay, so take the derivative of the unit step and you have a function that's everywhere 0 and a spike at the origin. The Kronecker delta is a function of two variables, 0 whenever the two arguments are different, the same 1 if the two arguments are the same, so that's a very well known discontinuous function. We can define piecewise functions either by combining the unit step, or there's also the piecewise construction that allows us to define discontinuous functions where the pieces can be continuous. Okay, so these are the main concepts that I want to demonstrate with the aid of SageMath. So let me swap the slides for the Jupyter notebook. So I will leave at the last slide because the last slide here actually contains a motivation for an exercise. So this could be a question on a quiz or an exam. Define a function like this. And how would you do this in the most appropriate way? Okay, so I have prepared a Jupyter notebook, and I will, if I kind of get stuck, go to this notebook, but allow me to start from scratch. So I will make a new notebook and build up what I want to explain step by step. So in this lecture 19, we define mathematical functions. So we look at functions not from the perspective of Python, but more from a mathematical, symbolic way. So my first section is to illustrate that functions are expressions. So there is little difference, but we can define functions explicitly. So for example, consider the following function. So we'll go over to the LaTeX notation. So I have a function in two variables. It will be a periodic function, but with a decaying amplitude. So the farther you go from the origin, the smaller the amplitude. So this is our mathematical definition, and I will leave up the LaTeX code a little bit because actually the LaTeX code is actually more complicated than the Sage definition. So, and again, this might be another way to work or to learn LaTeX. So there is the LaTeX operation. The only thing that you have to remember, of course, is that the multiplication symbol needs to be defined explicitly. And I made a typo in my definition, so let me fix that, but I first will execute. So here is the function that I wanted to define. So the typo that I made was in the y. So this looks different from an expression, but if I ask for the type, then it is essentially an expression. So I can turn this into an expression by symbolic evaluation. So I could use the variables x and y again, but that could be a little bit confusing. So let me declare new letters, u and v, new names of variables, and they will be represented by the letters u and v. So the expression that I make is by evaluation. So I will use the keyword arguments. I'm replacing x by u and y by v, and you see that now I have a regular expression, not a regular expression, a symbolic expression. So the e and the f, they are almost indistinguishable. I can go the other way around. So let's make a function g by substituting the u and the v by x and y. So x and y are the parameters of the function. It's natural to take x and y, but there's nothing that actually prevents us to use other letters. So I will define a function in x and y by evaluating the expression e symbolically. So note that e, so you have to know which is left, which is right. E has variables u and v, so I have to replace those. So this is another application of symbolic evaluation. So g is again an expression, but it looks like a function. So if you have forgotten what the variables are, you can actually ask. So there is the variables. So e is an expression, but the variables are also defined here. So that's important if you have many, not only if you have forgotten them, but suppose that you have many variables. So you can ask for them. So we can take derivatives. So why is it important to work with a mathematical expression? So on both the expressions and the functions, we can apply the method derivative and integral. So they are methods. So that means I could work with f, but let me work with g. I can take the derivative of g with respect to x, its first independent variable, or I can take the derivative of e with respect to its first variable, and that is u. Again, one can, if one doesn't want to do this, so you can, if you have forgotten the name, you could actually ask for it and select from that tuple, the first. So you see, it looks identical. To make the point, I can also take the antiderivative. So these are functions in several variables, but we are not scared of those because we have taken a course in multivariate calculus. Now, it took a while and the expression is a little bit inconvenient to read. So one strength, oops, so you see again I was careful but I was distracted. So taking the derivative, the antiderivative with respect to x didn't have make much sense. So I have to take the antiderivative with respect to u. So symbolic integration is both a strength, but then also a little bit troublesome because we will not go in there here. In symbolic computation, you can often get expressions that are hard to parse. The point here is not so much what is the value, the point is that on both functions and expressions we can ask for the derivative and the antiderivative. We cannot do that on Python functions. So let me make the distinction between expressions and Python functions. So we are running Python within Sage, so that's important. So we can define the same function. So let me, in a code cell, so let me, here is the definition again. So I can define my Python function. So let me call it p. So I have x and y, and I will return the exp, the exponential, multiplied with the sine of x plus the cosine of y. So when I hit run, all that happens is that the syntax is being checked and I didn't make any type errors. So the point being that we have an object p that is a member, an instance of the class function. So we can evaluate this function, but we cannot integrate or differentiate. So we can evaluate the function, but not integrate nor differentiate. So I can try it, but let's not do this. We will have a bug. So the point though is that we can evaluate, and within symbolic computation we can evaluate at a symbol. Because we are running Python, but we are running Python in SageMath, we can transform this Python function into a mathematical expression. In this context, all our expressions are mathematical. So let me do this. I still have the variables u and v sitting there, so I will use those. So I will replace the formal parameters x and y by u and v. So u and v have been defined prior. If not, one has to define them here. And now you see that I have an expression derived from the function. So here there's not much a point to it, because you could easily have retyped it, or even if you didn't want to type, you could do copy and paste. But if the functions are more complicated, and if you don't want to resort to low-level techniques, this is another application of symbolic evaluation. Okay, so we worked with our first example with a very nice continuous function. So let's look at step functions. So step function, step and piecewise functions. So there is the unit step. So let me define the unit step. Function is defined as follows. So you could see this also a little bit as rule-based programming. So if x is less than 0, then f of x is 0. F of x is 1 if x is greater or equal than 0. So we will see that this is the definition that the built-in unit step uses. So there is unit underscore step that is defined. So if I evaluate this at -1, I have 0. Unit step at 0 is 1, and unit step at 1 is also 1. Okay, so let me make a plot. So I will plot for x in the interval -1 to 1, and I will ask that the aspect ratio is 1. And let's see if I need to increase the thickness. So here we see the unit step function. Okay, so I said that it might make more sense to define the value at 0 at 0.5. So let me illustrate this. So we can see the unit, the step function, as the limit of another function, and that is 1 over 1 plus the exponent minus 2k times x for k going to infinity. Okay, so let me fix that still a little bit. So this is a definition of a function with a parameter and one variable, x. So x is the variable, k is the parameter. So no problem. So to define this, I will take the variable first and the parameter second, although it doesn't really matter. And typing this in is just as easy as I typed in the LaTeX definition. So here is the function. So and now let me make the plot for x, and I will take a value for k. 32 is just a good value. For x also between -1 and 1. I don't want that Sage is squeezing or resizing. And let me do the thickness also at 2. And now you see the point that I want to make, that this is a function. You see that this function behaves very much like the unit step function, although it's still a continuous function. If I let the 32 increase, so I can play with this, so let me double this to 64, then you will see that the function becomes steeper and steeper, and it will eventually touch the 1 at the top and also the 0 here. So one can see this unit step function then as the limit of this function h. So the limit of this function is also called the heavy side function. So the limit of the k for k going to infinity is called the heavy side function. Another important stepwise function or discontinuous function is the Dirac delta function. So if I take the derivative, so here is another way how to take the derivative, but don't worry, we will still have an entire lecture on differentiation. So the Dirac delta function is defined, so it's actually a function that is everywhere 0, except that it has a spike at 0, but here Sage does not really define this, so it's still left as a symbol. So if you plot it, it's kind of a flat function, but there is a spike in the middle. So on the slides I also mentioned another delta function. Is the Kronecker delta. So this Kronecker delta is typically defined for indices. So let me state what the rule is. So you would see this defined as follows. That's the first rule. And the second rule is that so for symmetry I will write it like this. So if takes 2, it takes on input 2 arguments, I and j. If they are different from each other, it is 0. If they are the same, then it is 1. So I can do the Kronecker delta of 1 and 1. This is 1, the Kronecker delta of 1 and 2. This should give me 0. Indeed. So these are predefined discontinuous functions. So this is a discontinuous function in 2 variables. Why are these predefined functions so useful? Because we can use them as basis functions to make more complicated functions. So here was the exercise. So let me go back to the slides. So I want to define this staircase function. So there are 4 rules. Let me type them in. I don't think I can put everything on the same slide. Or I will try, at least if I can scroll things up a little bit. I don't think that will work. Never mind, I will write the definition. So with the unit step, we can define a staircase function. So a more complicated discontinuous function. So let me set up the rules. So the first rule is that f of x is 0 if x is less than 0. So that's the same as the unit step. The second rule is that f of x is 1 over 3 for x in the interval 0, 1. So this is a half open interval. So at 0, the function is 1 over 3. At 1, I still have to define what it will be at 1. So there is a jump. At 1, I will have 2 over 3, and it will stay that way till we get to 2. So the third rule does not define what the function value will be at 2. So that's defined by the last rule. So I should have been a little bit more consistent. So instead of using the for, let me use the if. So this is not a programming class, but you can do this with a nested if-else statement in Python. Again, then the disadvantage will be that you cannot integrate and you cannot differentiate this. And I'm not entirely sure whether the symbolic evaluation will work. Because I may illustrate a problem with the symbolic evaluation. Okay, I have the following that I can do. I can add up the unit step function. So I can combine rule 1 and 2. So if forget about rules 3 and 4 now. If I just have rule 1 and 2, then this is essentially the unit step function divided by 3. So let me define f. So f of x, so it will be a function. It's the unit step x divided by 3. So we can compute with functions. So that will satisfy rule 1 and 3, but then I have 1 and 2, but then I have that when the x is larger than 1, I have to add also 1/3 to this. But this only starts to take into effect if x is larger than 1. So I can solve this via a shift. So I can subtract 1 and divide by 3. And perhaps for experimental reasons, I should probably stop and run this and make the plot. So if you do this, you can, so I'm interested in the range -1 to 3, and let me also use some thickness. So this plot will show that I'm on the right track. So I have correctly implemented rules 1. So rule 1 says that the function is 0 at the left side. In between 0 and 1, I have 1/3. And then larger than 1, I have 2/3. It's not entirely clear here, but you can see this is about twice the 1/3. Okay, so the rule worked, so I can apply the same shift when x is larger than 2. So x minus 2 is positive then I can add another third. And here you see the step function. So I have set up the rule in this way such that, so the rule is set up in this way that the unit step most likely takes the value 1. Yes, so we have said that the unit step at 0 is 1. So that means that indeed I have 1/3. So let me verify this. So f at 0 should be 1/3. And it is indeed. Also f at 1 should be 2/3. Indeed. So I can't really see from the picture if that is correct, but in order to verify the correctness of the definition, I should do this. Okay, so I have this definition here. I can make the same function, but with a more general construction. So I can use the piecewise. So with piecewise, we can also define indeed discontinuous functions, so piecewise functions. So some rules to know. So the piecewise takes on argument as a list. The argument of piecewise is a list of tuples. So the first argument of each tuple, so tuple with 2 arguments, so the first argument of each tuple is the interval. The second argument of each tuple is the value on that interval. And the intervals are either closed, denoted with square brackets, or open with round brackets. So why is that? Because the square brackets represent lists, and the tuples are done with round brackets. Okay, so I want to solve the same problem. So let me take this problem again and copy and paste. So here is what I want to do. So I want to use piecewise to define the same function. So here is now the task. So here is the exercise. Use piecewise to define f following the rules below. So that was the last exercise on my slides, the last example on my slides, and I have ample time to do this, I hope. So piecewise, so I will again use f, but perhaps let me use capital F now. Piecewise. It takes on input a list of tuples. So the first one tuple gives me the range minus infinity, 0, it's an open interval, and there I have the value 0. So that is my first interval. So the minus infinity and the plus infinity are predefined. And then I have my second interval, which is a closed or half open, half closed. How do I define that? Well, I start with the special value 0, where the value is 1/3. And then I have the interval from 0 to 1, where the value is actually also 1/3. So now I have the first two rules implemented, and again I can continue typing, but that's not a safe practice. So let me make the plot and verify whether I get the desired effect. The piecewise is a little bit more complicated, it seems, so it takes Sage a little longer to plot this. And okay, so here is my fault as well. The 1 was not defined, so I should have used 1. So let me redo this. Then I don't have Sage complaining. So I should see a similar unit step function indeed, and here you see that it stops at 1/3. So my definition here is correct. I have the first two rules. So let me continue with the next tuple, which is again which has to be broken in two. So I have the next tuple, which will include the point, define the point 2, and there I have 2/3. And let me continue with the interval. I have too many brackets here. But now the interval, I went too fast, so this is 1, 1, and then I have the interval, open interval 1, 2, where the function value is also 2 over 3. And I hope that this went well. Apparently it did. And now I can check the plot. Change the range where I want to see the plot from -1 to 1 to -1 over 2. And here you see that I have now also rule 3 defined correctly. So I ended with the open interval 1, 2, and also defined the point 1, 1. So that's an interval that has only one point in it. So it's a little bit more typing, but it's more general. So let me do the last interval. Well, actually I have 2 more to go. So I have to define that the point, at the point 2, I also have the value 2 over 3. And then the last half open interval starts from 2 to infinity, and there I have also the value, I have the value 1. So I have the value 1 here and the value 1 there. So this is the combination, this is essentially the rule 4. I cannot work with so here rule 4 looks like a simple rule written down mathematically, but I cannot include infinity. So it would be wrong to have 2 comma infinity with the square brackets. So I have to define 2 separately, and then the half open, and then the interval 2 to infinity is a open interval. Okay, so let me define this and make the plot. Okay, so this is hopefully gonna work out fine, and indeed it is fine, except that I forgot to adjust the range. But that plot was essentially also good, because you could see that at 2 I had the function value 1, so I removed it too quickly, but here you see the final result. And as before, I should essentially check what happens at 1 and at 2. Okay, so I hope this was interesting. I encourage you to look at the exercises in the notes as well, because in summer our midterm exam occupied 2 lectures. In the lecture notes, they are still for the regular semester. The material in this lecture corresponds to lecture 18. So for the lectures here, we have to subtract 1 in the lecture notes. So one last thing, let me scroll up. So here you see the entire piecewise, how it was executed. So for I could have probably done this a little bit better in one statement, but I would encourage you to look at the posted notebook that will be posted at the course website. Okay, I'm running over time, or almost. I'm closing off. I hope this was interesting.